Alright, thanks for watching. And today we'll do a very interesting optimization problem which says the following. I know it's very long, but you'll see it'll be worth your time. So a grain silo consists of a cylindrical tower surmounted by a hemispherical dome. The material of the dome costs 50% more per square meter than for the cylindrical tower. If the volume of the silo is 750 cubic meters, find the dimensions of the silo, so radius and height of the tower, that minimize the cost of the silo. And assume that that silo has no floor and no flat ceiling under the dome. Here's the thing about the optimization problems. They're very long to read, and there's a lot of information just thrown at you. And really, the best way to deal with those optimization problems is to dissect that problem. In other words, figure out what information it gives you and what information is important and not important. Sort of similar to an archaeologist who is excavating some tomb. Well, that person would find some bones that are valuable and not valuable. And the person needs to figure out which ones are important, which ones are not important. And it's the same thing for this word problems. Alright, so we need to figure out kind of the skeleton of the problem. So let's see what kind of information is given. So first of all, we know that we have a grain silo that has a cylindrical tower with a dome on top. So that's already very important to draw a picture of it. So this is the first information that this gives us, which is a picture. So this weird thing, what it looks like a cylinder. And on top is a dome. So I'm sure you've seen those things before. Again, if you're interested in grains or rice, so you might have seen that on the highway. And that's the first thing. Again, it gives you information. It tells you we have a cylinder on top and a hemisphere on top. Then let's look at the second piece of information that's given. 2. The material of the dome costs 50% more per square meter than for the cylindrical tower. So it is important information, but it's something we'll use later because it doesn't tell us yet how to solve the problem. But let's just write this on our picture, that this part is more expensive than the other part. So again, you have two things. We have the cylinder part and the dome part. And just know that the dome part is more expensive than the cylinder part. And again, the first step is the picture. Okay, that's already very good. Then the next piece of information, we know some information about the volume. So the volume is 750 cubic meters. That's also important information, but something we'll use later. So just right now, just note this as note. We know that the volume is 750 cubic meters. Again, right now doesn't help us because it still doesn't tell us what we have to do. But now the next step tells us what to do. Namely, the heart of the problem is the following. Find the dimensions of the silo that minimize the cost of building it. So this is very important. This gives us the instructions of what to do. And we'll use that in a second. But last thing, let's finish the reading of the problem. So assume that the silo has no floor and no flat ceiling under the dome. This one is not very important information because I'll mention this later. It just tells us that the way we'll do it is the correct way. Otherwise, if the opposite were true, then we would have to work a little bit harder. So you see, this one looks like a nightmare to do, but once we dissected it, it actually becomes more reasonable. This tells us, draw the picture. This gives us some information about the dome. This info we'll use later. We'll keep it in the back of our heads. This one is the most important one, which gives us instructions of how to do the problem. And this one just gives us some reassurance that what we'll do is correct. Okay, now let's look at what we have to do. We have to find the dimensions of something that minimize the cost of building the silo. So it seems that in this case we have to minimize a sort of surface area. So let's now calculate the surface area of that cylinder and the surface area of that dome. So that leads me to the second step of optimization problems. So the second step is we want to find some function that we want to maximize or minimize. And for this we need to use actually all the info that's given to us. So part 2, functions. Again, the goal is to minimize a sort of surface area. And for this, we need to introduce some variables, which, by the way, are already given to us in the problem. The problem tells us we need to use the radius of the cylinder, which is r, and the height of the cylinder, which is h. So again, just to clarify, let r be the radius of the tower. And h be the height of the tower. So in those problems, it's very important to define what variables you have. So here r is the radius and h is the height. So first of all, let's find the area of that cylinder. So area of cylinder. You have to be very careful here, and in fact that tricked me as well. So we don't want to, it's not pi r squared times h. That would give us the volume of the cylinder, but what we need is just the area. So what do you have to do? You have to take the circumference of this circle, so 2 pi r. Again, just the circumference of this circle. And you have to multiply this by the height, because you're essentially having a bunch of circles piled up and kind of h of those, more or less. So again, it's just 2 pi r h. So that's the first thing. That tells us, the area of the cylinder, and then the next part is to find the area of this dome, and just recall. Okay, so surface area of a sphere of radius r. Again, suppose you have this sphere of radius r. That's just 4 pi r squared. Now, couple of things. Why did I write r here? The same one. In theory, it could be a different radius, but notice, well, actually the radius here, it's the same thing as the radius on top. And that's actually very good information, because now we know that this hemisphere, we don't need to define a third variable for its radius. Okay, so this is the surface area of a sphere, but of course, because we have a hemisphere, we have to divide it by 2. So area. So in other words, area of dome is just 1/2 of that. So 1/2 of 4 pi r squared which is 2 pi r squared. Okay, so what do we have? We have the area, if you want, of the tower, which is 2 pi r times h, and we have the area of the dome, which is 2 pi r squared. And of course then, you might think, okay, it's true that the surface area of the tower then is this plus this. But careful, this is not quite the cost of your tower, because, and again, this is why our little note was very useful. Remember that the dome is 50% more expensive than the cylindrical tower. So what we have to minimize is not this plus this, but this plus, again, 50% more than that. So 1.5 times that. So, and that almost brings us to our function. So, in other words, the total cost is again the area of the cylinder plus, again, 1.5, so 3/2 times the area of dome, and again, this 3/2 accounts for the fact that it's 50% more expensive. So what this becomes then, it's again 2 pi RH plus 3/2 times 2 pi r squared, which becomes 2 pi RH plus, you see the 2's cancels out, and you get 3 pi r squared. Okay, one little remark. Remember, there was this last sentence that said, assume, what was it? Assume that the silo has no floor and no flat ceiling under the dome. What this is telling us is, again, some reassurance that this we have to minimize. Otherwise, if they said that the top and the bottom mattered, then we would also have to add the area of this circle and the area of this circle. But this is telling us, no, we don't have to worry about this. That's why I said it's important information, but you can really put it at the lowest floor of importance. Okay, very good. So far we've figured out the stuff we want to minimize, but the only problem is this depends on two variables, r and h, and this is not multivariable calculus, this is single variable calculus. So let's try to go from there and transform it into a one-dimensional problem with just one variable. And for this, there is still one piece of information that we haven't really explored yet, which is the volume thing. Which actually, so it reminds me, it's not Dora the Explorer, but this time Doma the Explorer, because we have a dome. And so, again, the problem is, this depends on two variables. This depends on r and h. And what is the solution to that? Use the fact that the volume is 750 cubic meters. Okay, well, and let's just calculate the volume of the tower. So I would like to remind you, the tower is just a cylinder plus a dome. So the volume itself, it's the volume of the cylinder plus the volume of the hemisphere. So let me just remind you, so the volume of cylinder. Again, this time it's not 2 pi RH, but what you do, you take the area of the circle, which is pi r squared, and you multiply this by the height. Because again, you're kind of adding up a bunch of little disks of height h. And then, for the rest, remember the volume of a ball. So we call volume of sphere. It's, again, a sphere of radius r. It's 4/3 pi r cubed. So in other words, the volume of the dome, it's half that. So 1/2 times 4/3 pi r cubed. And what this becomes, it's 2/3 pi r cubed. And therefore, what do we have? The total volume, which is the cylinder plus the dome, is just the sum of the two. So V equals pi r squared h, I get cylinder, plus 2/3 pi r cubed, which is dome. And what do we know? We know that this is 750 cubic meters. And that's very good, because this gives us extra information. It gives us some information for which we can solve one variable in terms of the other one. And the question is, which one do we solve for? Because we have two choices. We can do r in terms of h, or h in terms of r. The only problem is, if you use r, in terms of h, then it becomes quite messy. You have cube roots, square roots, and in fact, I believe it's not even possible right now to solve it. But it's much, much easier, and that's what we'll do, to solve for h in terms of r. So solve for h in terms of r. So what do we get? We get pi r squared h equals 750 minus 2/3 pi r cubed. And then h, you just divide by this. So h becomes 750 minus 2/3 pi r cubed divided by pi r squared. So you're dividing by pi r squared. And then let me just make sure this is correct. So what we get? H, it's 750 over pi r squared. And then minus 2/3 pi r cubed over pi r squared. And what's nice about this is that the pi's cancel out. And then one of the factors, so this r squared cancels out with r cubed to become r. And then what we're left with is simply 750. Maybe let me write that on a new board, new part of the board. So h, it's 750 over pi r squared minus 2/3 r. And that's wonderful. We wrote h in terms of r, again, without much effort. You just solve this simple equation. And this extra information will allow us to write our quantity, the cost, in terms of r only. So, and again, we're still at step 2. I just want to remind you. So now, what do we know? The total cost again, it's 2 pi RH. And then plus, what was it? Plus 3 pi r squared. And now we can just plug that back in. So we get 2 pi r h, which is 750 over pi r squared minus 2/3 r plus 3 pi r squared. Now, expand this out, so what we get? 2 pi r times 750, so I think 1500 pi r over pi r squared, and then minus, so 4 pi r over 3 times r plus 3 pi r squared, and then we have some simplifications. The pi's cancel out, the r cancels out, and then we get r squared. So I think what we're left with is 1500 over r plus, I'm sorry, not plus, but minus. Erase that as well. Luckily, we won't need that anymore. Minus 4/3 pi r squared, and then plus 3 pi r squared, which is quite nice. There is this common factor of r squared here, which means we can simplify things a little bit. So this becomes 1500 over r, and then plus, if we want, minus 4/3 pi, or no, minus 4/3, yeah, plus 3 times pi r squared. And if you want, this is minus 4/3 plus 9/3. So in the end, we get 1500 over r plus 5/3 pi r squared. So, as Borat says, great success, because we finally found the function that we want to minimize. And this is where we find, as an archaeologist, that very important bone, because we really use up all the information that we needed in order to find this function. So the rest is really just pure calculus. How do you minimize this function? So in other words, f of r, it's 1500 over r plus 5/3 pi r squared. And now, step 3. Minimize f. Remember, the important trick to minimizing a function, it's really finding the critical points of your function. In other words, points where the derivative is either 0 or does not exist. So now let's calculate f prime. So f prime of r. Again, the 1500 comes out. And now the derivative of 1 over r, it's minus 1 over r squared. And then plus 5/3 pi, and the derivative of r squared, it's 2r. And so what we're left with is minus 1500 over r squared plus, if you want, 10/3 pi r. Okay, and here's the thing, sure you can set it to equal 0, but it turns out, and this will be very useful in a second, it's put it on a common denominator. So what we get is, again, minus 1500 times 3 over 3r squared Because here we have an r squared, here we have a 3. So to put it in a common denominator, multiply this by 3 and multiply the bottom by r squared. So 10 pi r times r squared over 3r squared. And what you end up with is minus 4,500 plus 10 pi r cubed over 3r squared. And now you want to set it equals 0 because we want to find the critical points. We want to figure out when f prime is 0. Okay, and what do you do? Well, first of all, you want to guarantee that the denominator is non-zero. But look, it is non-zero because the only point that makes the denominator 0 is 0, but f isn't even defined at 0. So we can just eliminate this. So really, all that we need to do is to figure out when the numerator is non-zero. So minus 4,500 plus 10 pi r cubed equals 0. And that gives you 10 pi r cubed. It's 4,500. So we can divide everything by 10. So pi r cubed, it's 450. And I'll just solve for this. So again, r cubed is 450 over pi, which gives you r, its cube root of 450 over pi. If you want meters, just to be consistent with the units. I know it's not the nicest of answers, but we get also a nice answer actually for h. And again, very important. It's not enough just to find the critical points, because this doesn't really give you the answer, because it could possibly happen that this actually is a maximizer. So, something forbid, we could have that this is the highest point of the function, even though it is a critical point. So really, what we want to make sure is that indeed this minimizes the function f. And usually what you do is you plug in the endpoints or use a second derivative test. That's just for local things, by the way. But here the only problem is there are no endpoints. So r can be as big as infinity, it can be as small as 0, because that's just the way that the problem is designed. And therefore, for this, we need to use a new theorem, which is called the first derivative test for absolute extreme values. For absolute extreme values. Abbreviated as FDT AEV, or FTAEV, okay? And what does it say? Actually, something very simple. And let me illustrate this with a picture. So suppose you have a critical point at C, and your function f is decreasing up to C and then increasing, then C, f is guaranteed to have a minimum at the point C. And similarly, if f is increasing before C and then decreasing after C, then f has to have a maximum at C. So let's just write this in terms of math. So suppose f has a critical point at C. meaning that either f prime of c is 0 or f prime doesn't exist at c. And so, first of all, if f prime, so in other words, if f is decreasing before c for r less than c, and f prime of r, it's positive after c. So again, suppose we have the case where this is r. So f prime is negative up to c and then positive after c, then f has an absolute minimum at c. In other words, the lowest value ever of f is at c, and similarly, if f prime of r is positive for r less than c, and f prime of r is negative for r greater than c. So again, if f is increasing before c and then decreasing after c, then f has an absolute maximum at c. Alright, and so now let's apply it to our function. So again, the critical point here is cube root of 450 over pi. So here, see, it's cube root of 450 over pi. So if r is less than c, so if r is less than cube root of 450 over pi, then unfortunately I erased our function, but we want to show, in other words, because it's a minimum, we want to show f prime is negative. So I would like to remind you that f prime of r is nothing else than minus 4,500 plus 10 pi r cubed over 3r squared. So except it's a plus here. So all you need to show is that you want to show this is negative, but notice the denominator is positive. So all you need to show is that the numerator is negative. So let's take this. We first want to have 10 pi r cubed. So then cube r, so r cubed is less than this thing, cube root of 450 over pi cubed. So, and then cube, which becomes 450 over pi. So then 10 pi r cubed is less than 10 pi times 450 over pi. This cancels out, which is 4,500. And then if you subtract 4,500, you get that it's negative. So 10 pi r cubed minus 4,500 becomes negative. And so f prime of r, which is minus 4,500 plus 10 pi r cubed over 3r squared. Again, as I said, this is always positive. We've just shown that this is negative. So this whole thing is negative. In other words, what have we shown? Then if r is less than the critical point, then f prime is negative. So f is indeed decreasing up to your critical point. And similarly, you can show if r is greater than the critical point, then f prime of r is positive. So really, by this FTAEV, so f dt AEV, f indeed has a minimum. At your point R, which is cube root of 450 over pi. So now you can say with confidence that the smallest value of f is at the point cube root of 450 over pi, but unfortunately that's not quite what the problem is asking, because the problem isn't just asking for r, but it's also asking for h. And by the way, be very careful when you read those kind of problems, because sometimes the problem is actually also asking you for f, so the smallest cost. But here that's not what we have to find. We have to find h. So if you want step 4, in conclusion. Okay. So found r equals cube root of 450 over pi, which again, if you want, you can write it as 450 over pi to the 1/3. And now all we need to do is find h. But here's a nice thing. We already have h in terms of r. So use the fact that h, it's 750 over pi r squared minus 2r over 3. Actually, I wonder, did I put it under the common denominator yet? Unfortunately not. So let's put it on the common denominator first. So we get 3 times 750 over 3 pi r squared minus 2r times pi r squared over 3 pi r squared. Again, r is ugly so far. Let's see what happens to h. And you'll see it's quite a beautiful result. So 3 times 750, I believe it's 2250, minus, I think, 2 pi r cubed over 3 pi r squared. And all you have to do is plug in your formula for r inside of this. And it becomes quite messy, so let's split up the numerator and the denominator. So the numerator, what this is, becomes 2250 minus 2 pi r cubed. So 2 pi cube root of 450 over pi cubed. That becomes 2250 minus 2 pi times 450 over pi. That's quite nice. The pi's cancel out. And you get 2250 minus 900, which I believe gives you 1350. Which I was very surprised by that, but you'll see it's quite crucial in a second. So that was the numerator, and now let's focus on the denominator. So 3 pi r squared, which is 3 pi times this thing squared. And that's why I wrote this in terms of powers. So 450 over pi to the 1/3 squared. And that becomes, so 3 pi times 450 to the 2/3. So 450 over pi to the 2/3, which you can just split up. So 3 pi to the 450 to the 2/3 over pi to the 2/3. But look, this kind of comes together because pi, it's pi to the first power. So this thing you can simplify a little bit. So this becomes 3 pi times 1 minus 2/3 times 450 to the 2/3. And that becomes 3 pi to the 1/3 times 450 to the 2/3. Which is good. So now we have our two expressions. We have the numerator, which is 1350, and we have the denominator, which is this gibberish. And now all you have to do is take the ratio of that. So then h, it's 1350 divided by, again, 3 pi to the 1/3, 450 to the 2/3. But here's the nice thing. So 13, and again, this is the miracle that I didn't really believe in at first, but it is actually correct. If you divide 1350 by 3, it turns out you get 450. So equals, and again, that's what makes it work. You get 450 over pi to the 1/3, and then 450 to the 2/3. And again, 450, it's 450 to the first power. So this simplifies, and you get 450 times 1 minus 2/3 over pi to the 1/3, which gives you 450 to the 1/3 divided by pi to the 1/3. But what this becomes, it's 450 over pi to the 1/3. Which gives you h, but notice, this is the beautiful thing, it's the same thing as r. Oh my god! So in other words, what's the grand conclusion? The optimal silo has the property that the height equals to the radius. So let's see, grand conclusion. So r equals h equals cube root of 450 over pi, and again with the units it just becomes meters. In other words, an optimal silo, what it looks like this. So this is, if you want, the radius. So this is r, and then the height, it's the same thing as a radius. So you see, not too big because then it would be too expensive, but also not too small because you want the volume to be 750 cubic meters. And that's the nice thing. This is the nice thing about optimization problems. In other words, the optimal shape usually has some sort of a symmetry in it. For instance, if you ask for, let's say, a rectangle with a given perimeter, and you want to, I think, either minimize or maximize the area, the optimal rectangle becomes a square, you know, or like usually an optimal triangle is an equilateral triangle. Here, the optimal silo has the property that r equals h. I mean, isn't it beautiful how nature just works out? Like, we like symmetry in nature. Last but not least, there's one thing I want to mention, because this way I did was very messy, right? You had a bunch of cube roots and everything, but it turns out there's a much more elegant way of doing this using implicit differentiation. So let me show you the oh my god way. Now, remember we had the cost. Let's call it C, which was 2 pi RH plus 3 pi r squared. C, or I guess even F, you could call it like that. Okay. On the other hand, we also know that the volume, which is pi r squared h plus 2/3 pi r cubed, that's 750. Again, it's all the info that's given to us. Now, how about, look, r is r, and h, strictly speaking, is a function of r. We literally solve for the h in terms of r. So one thing you can do, you can differentiate this equality with respect to r. So c prime, what this becomes is 2 pi rh prime plus 3 pi r squared prime, where again prime just means differentiate with respect to r. Okay, now again r is a function of r, h is a function of r, so let's just use the product rule, or I like to call it the Prada loop. So we get 2 pi times 1 times h plus 2 pi r h prime, and then plus, so 3 pi times 2r, which in the end gives us 2 pi h plus 2 pi r h prime plus 6 pi r. Now here's the thing. So c, again, is a function of r. So in particular, at the minimum, we need to have the critical point. So at the minimum, this actually becomes 0. So we can just set this to be 0, and we can actually simplify this a little bit. So if you divide by 2 pi, this cancels out, and this becomes 3. So I believe what you left is simply h plus rh prime plus 3r equals 0. That's the first identity that we have. On the other hand, we can do the same spiel with v, because v is always constant. So if you differentiate all the sides with respect to r, the right-hand side becomes 0. So let's see. So we get pi r squared h prime plus 2/3 pi r cubed prime, and that's 750 prime. And yesterday I had USDA prime, and what you end up with is, so the again product rule, so pi times 2r times h plus pi r squared h prime, and then plus 2/3 pi, and then 3r squared equals 0. This simplifies, and so we get, if we want 2 pi rh plus pi r squared h prime plus 2 pi r squared equals 0. Now here again, the nice thing is we can cancel out the pi's, and then we can also cancel out one factor of r. So divide by r, this disappears, and then what you end up with, let me just check. So yeah, 2h plus rh prime plus 2r equals 0. So we get two pretty simple equations, and all we need to do is to just play around with this. You can spiel mit mir, and we get, again, h plus rh prime plus 3r equals 0, and 2h plus rh prime plus 2r equals 0. And that's the beautiful thing. Notice there's this common factor of rh prime. And so just subtract. So h plus rh prime plus 3r minus 2h plus rh prime plus 2r. It's just 0 minus 0, which is 0. So h plus rh prime plus 3r minus 2h minus RH prime minus 2r. It's 0. So this cancels out. And then what we end up with is the following. So h minus 2h, that's minus h. And then 3r minus 2r, that's r. So minus h plus r, it's 0. And so we get, again, like before, that h equals r. How pretty! And then you can just solve for r, for instance, using the fact that the volume is 750 cubic meters, or, yeah, I think that's the main thing what you can do, yeah, in this case. Alright, I hope you like this little optimization extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.